Hello everyone. Today I am going to present my work on computational fluid analysis of flow losses in globe wall. The work has been carried out under the supervision of Professor Anupam Diwan and Professor Vinod Narayan. This will be the brief outline of the presentation. I will begin with the introduction, then move on to the computational methodologies, discuss the geometric and meshing details, followed by the resultant discussion and the important conclusions from this work. Now beginning with the valves, a valve is a device that is used to helps to regulate, control or direct the flow of fluid in a pipes. So basic operations of the valve involves opening or closing or partially obstructing the flow of fluid. So depending upon the function, valve can be used for a variety of application. For example, basic function is the starting or stopping of the fluid flow, or varying or maintaining a definite amount of fluid flow, then changing the direction of flow, or changing the fluid pressure, or relieving the piping system from excess pressure. Now talking about the globe valve, it is a special kind of flow control valve which is used in wide variety of engineering application. The name globe valve is because of the shape of the valve, which is hemispheric in shape. Large pressure drop occurs through the valve because of sudden restriction in the geometry, so this gives rise to rapid changes in flow direction also, and due to this the complexity of flow passages, the flow features which are generated inside the valve are very complex, and it is almost difficult to visualize such flow features through experimentation. So under such constraints, CFD has emerged as a cost effective tool to analyze such complex flow features. Flow losses occur in the globe wall due to fluid friction, as well as the friction between the piping surfaces and the sudden changes in flow path of the fluid within the wall. So these flow losses are evaluated in terms of various performance parameters. The performance parameters which are checked in this study are the loss factor and the flow coefficient. So loss factor basically represents the head loss through the wall to the velocity head which is associated with the piping system, whereas flow coefficient is a measure of efficiency of the valve which is used to compare different valves. So now coming to the computational methodology which is used in CFD is basically the equations, Navier-Stokes equations for an incompressible fluid are solved in the flow solver. These are basically the continuity equation and the momentum equation, and the Reynolds stress terms in this are modeled through Rand's equation model. In this work, K epsilon turbulence model is being used because it accurately captures the spreading rate of jets and the complex flow features which are encountered in globe valve. The solution methodology adopted for this is that the convective and diffusive terms were discretized using the second order central difference and second order upwind schemes respectively. So the three main questions which we are trying to explore in this study is that first is the how the variation of the loss coefficient and flow coefficient takes place with respect to Reynolds number for a given valve opening. In the second question we are trying to see the influence of valve opening on the loss factor. In the third question we are trying to explore how the changes in the orifice diameter has an impact on the loss factor. So these are the geometric details of the valve. We can see that the three main parameters are the valve diameter, which is capital D, small d is the throat diameter or orifice diameter, and capital H is the valve height. So the valve geometry as shown in this figure was made in AutoCAD, and then this geometry was modeled in two domains. The first is for the inlet pipe, which is to get the fully developed flow, and the second is the valve geometry. So this shows this computational domain which was used in star CCM. So this is the domain 1, which is the same as that of the valve diameter, and the second domain is the valve in which flow within the valve was modeled. So in this first domain, periodic boundary conditions were specified at inlet and outlet, and initially a uniform velocity profile was given at the inlet. This velocity profile developed in the fully developed profile as can be seen from this simulation. So when we obtained a fully developed profile in this, then this fully developed profile was given as an input for this second domain, and the walls were modeled as no slip adiabatic boundary conditions, and the outlet of the wall was specified as pressure outlet. So the complex flow features which are created within the wall can also be seen in this streamlines. So this is how the flow occurs within the wall. And the operating conditions for three different sets as described before for three different questions are: in the first set, Reynolds number was varied; in the second set, the valve opening or stem height was varied from 6 to 31 mm; and in the third set, we varied the throat diameter from 6 to 18 mm to study their impact on the loss factor. Now this shows the meshing domain which has been used in star CCM. Again, this shows the cross section of the pipe which was modeled. So we can see prism layer near the wall and unstructured grid, hexagonal grid which was used in this. And for the wall geometry, we can see that mesh refinements were used near the wall plug and the steam height and the orifice so as to capture the fine details. We also performed a mesh convergence analysis, and we have chosen a size of 1.2 million cells at which the flow coefficient there were no changes in further flow features. And similarly, the other parameters which have been used in star CCM are listed in this table. Now coming to the results and discussion, we can see that the fully developed velocity profile which was obtained after domain 1 in this figure, and this shows the velocity profile when this profile was input for this domain. We can see there is a flow acceleration in the orifice which is due to the sudden contraction of the flow path, and this increases the velocity here. And similarly, there is a loss of pressure, sudden loss of pressure taking place due to the orifice, and this shows the velocity vectors which shows the formation of recirculation zones etc within the wall. So we can see that the fluid flow is very complex, and due to the changes in sudden flow path, various losses are expected to take. So this slide shows the effect of variation in loss factor and flow coefficient and pressure loss with respect to the Reynolds number. So we can see that in the viscous regime or laminar regime, we can see that viscous losses are contributing mostly despite small pressure loss at this regime. So this creates a large loss factor which is observed in the laminar flow, whereas as the flow approaches the turbulent regime, due to the variation in pressure loss which occurs almost linearly with velocity, so this it decreases the loss factor despite increase in the pressure loss within the valve. So this causes a reduction in turbulent regime loss factor in the turbulent regime, and it becomes almost constant after a certain Reynolds number. The following figure shows the variation in loss factor with respect to the distance of the plug or the stem height. So stem height controls the flow of fluid in the valve, and we can see that on increasing the stem height at a fixed Reynolds number, the value of friction factor decreases almost linearly. So this occurs due to the reduction in the flow resistance or the flow path. And one important fact which we need to take from this is that the forces on the actuators will also vary due to these losses. So reduction of the loss factor will decrease the forces, and this must be kept under design consideration while designing the automatic actuators to open the valve. So now the effect of increase in throat diameter is shown in this figures. We can see that when the throat diameter is less, the velocity is more, but as we increase the throat diameter, the velocity maximum increase in velocity decreases, although the recirculation pattern are maintained in each and every flow. So we can see that the loss factor as a result decreases. So this occurs due to the less obstruction as we increase the throat diameter, and also the less kinetic energy loss which takes place. So depending upon the application, when throttling action is required, we should choose a small diameter valve, whereas for other purposes we can choose a larger diameter valves. So the following basic conclusions can be drawn from the work. Pressure losses for a given valve opening is a strong function of the Reynolds number. As the flow enters the turbulent regime, the pressure losses across the valve increases sharply. The loss factor was also found to be high in laminar regime, and it became constant for the turbulent regime. The loss factor is sensitive to the valve opening and the throat diameter, and it decreases on increasing these parameters due to the reduction in flow obstruction. So in future, CFD can thus be used as an effective tool for conducting various parametric studies to design and select the globe valve operation on the basis of their applications. These are the references used in the work. Thank you.